In the silence between galaxies, far from the warmth of starlight and the echoes of ancient worlds, there are places where even light forgets to wander. Here, in the shadows of the universe, something stirs, something vast, invisible, and hungry. Imagine drifting alone through intergalactic space, where the stars have grown faint and time itself feels sluggish. And then, a tremble. A ripple, not in air, not in water, but in space itself, a wave in the very fabric of reality. What causes the universe to shudder like that? What kind of event can bend space-time like wind on a pond? Before we begin, tell us in the comments where in the world you're watching from and what time it is there. It helps us feel just a little closer across the cosmos. At the heart of this mystery are black holes, cosmic phantoms that defy our most sacred rules of understanding. Born from the death of massive stars, they are the final stage of matter crushed under its own gravity. So dense, so powerful, that not even light can escape them. They do not glow, they do not radiate, they erase. And yet, despite their invisibility, we have found ways to see their presence. Not with eyes, but with patience. We watch how stars orbit invisible centers. We detect X-rays from hot gas spiraling in. And now, thanks to the language of gravity itself, we can hear them. But what happens when two of these titans meet? In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected something never before observed. Two black holes, over 1 billion light-years away, spiraled into each other. Their mass, their gravity, their momentum all collided in a violent, silent dance. For a fleeting moment, they created a storm of gravity so intense it sent ripples across the universe, ripples that we caught here on Earth. It was the first direct evidence of gravitational waves, a phenomenon Albert Einstein predicted a century earlier but believed too faint to ever be detected. These waves are not like sound or light. They are distortions in space-time itself, compressions and stretches that move through everything, including you, at the speed of light. To detect them, scientists built a machine of staggering precision. LIGO uses laser beams bouncing between mirrors spaced kilometers apart. If a gravitational wave passes through Earth, it changes the distance between these mirrors by less than the width of a proton. And yet, we heard it. A tiny chirp in the data, a flicker in the void. The two black holes had been circling one another for eons. As they spiraled inward, their orbit quickened. Like ice skaters pulling their arms close, they spun faster, faster, faster until they touched. And when they did, they merged. Not quietly, but in a cosmic crescendo. A final burst of gravitational energy spread out in all directions. And then a new black hole was born, more massive than the two before, with a perfectly round, silent event horizon. These collisions are common in the grand timescale of the universe. In some cases, they happen at the centers of colliding galaxies, where supermassive black holes, billions of times the mass of the Sun, are drawn together in gravitational embrace. In others, they occur in stellar graveyards, where remnants of exploded stars find each other again, locked in fatal attraction. Yet, not all black hole collisions are the same. Some are between giants. Others involve the quiet, slow pull of smaller bodies, drifting through the void. The scale changes, but the choreography remains eerily familiar. Orbit, spiral, merge. Each collision writes a different verse in the gravitational song of the cosmos. Still, not everything about this process is understood. Some scientists began to wonder, what if these collisions leave behind more than just a larger black hole? Could they twist space-time in ways we haven't yet imagined? Could they create wormholes, or even momentary gateways to elsewhere? There is no light, no radio signal, no chemical trace, only gravity remains. And gravity, as we now know, can carry secrets across eternity. There are even theories radical, speculative that black hole collisions might affect the structure of space-time beyond our visible universe, that they could send shockwaves not just across galaxies, but across dimensions. Theoretical physicist Juan Maldacena and others have explored ideas like the holographic principle, which suggests that what we perceive in 3 dimensions may be a projection from a deeper, more fundamental layer of reality. Could black holes be keyholes into that deeper truth? The equations are precise, But the reality they describe is almost mythological. A collision between black holes releases more energy in a few seconds than all the stars in the observable universe combined, not as heat, not as fire, but as pure warps in spacetime. And what if such energy could leave more than just ripples? Could it, under rare and extreme conditions, tear the cosmic fabric itself, exposing something behind the veil? What kind of universe are we living in, where such collisions can occur, where silence can roar and darkness can clash? Physicist Kip Thorne once said, "When two black holes collide, it is like a drumbeat in the fabric of spacetime." But whose drum is it? What is it keeping time for? And who or what might be listening? If gravity waves are the music of the universe, then black hole collisions are its symphonies wild, brief, and utterly unknowable. We think of black holes as the end of things, but when they meet, something new is born, a bigger void, a deeper silence, a signal traveling for billions of years just to whisper in our instruments. And perhaps, in the distant future, intelligent beings will look back and read these signals the way we read the fossils of ancient seashells, echoes of a dance too large to see, too brief to remember. For now, we watch, we listen, and we wonder, what else stirs in the darkness? What if two black holes collide and something we've never imagined comes through? When two black holes collide, the universe doesn't explode, it breathes. The tremors pass, the ripples quiet. The vast, invisible shockwave stretches out across the cosmos until it fades into silence once more. And in the wake of that collision, where once there were two ravenous beasts, now there is one, larger, smoother, utterly still. But this silence is not emptiness, it is potential. The newborn black hole forged in a moment of violent union is not just larger in mass. It is different, it spins, and that spin carries information, memory, momentum. Physicists call this a Kerr black hole, one that rotates with astonishing force. Some of them spin near the speed of light. And around such a rotating black hole, strange things happen. There is a region outside the event horizon, a twisted halo of distorted space known as the ergosphere. Here, space-time itself is dragged along by the black hole's rotation, a concept so alien it feels like fiction, frame dragging. Inside the ergosphere, nothing can remain still. Even light must orbit or be flung away. It is as if the very fabric of reality is caught in the whirl of a cosmic whirlpool. Some scientists believe energy can be extracted from this spin not by touching the black hole itself, but by dipping into this twisted space. This is known as the Penrose process, named after Sir Roger Penrose, who imagined it in the 1960s. He proposed that if you throw something into the ergosphere just right, it might split into two, one piece swallowed, the other flung out faster than it went in. A paradoxical fountain of energy drawn from the darkest source. Could this be how advanced civilizations far older than ours might power their technologies? Could a black hole be more than a grave? Could it be a wellspring? After a collision, the new black hole radiates not with light, but with gravity. It settles. It rings. This ringing is called a quasi-normal mode, like the chime of a giant bell. The shape of the tone tells us the mass and spin of the black hole. By listening carefully, physicists can tell whether the collision followed Einstein's predictions or if something else occurred. So far, the observations match general relativity, but just barely. Some gravitational wave signals hint at echoes, faint whispers that arrive just after the main chirp. Are they noise or something more? A few researchers speculate they could be the signs of quantum corrections near the event horizon, or even structures beyond the black hole, so-called firewalls or fuzzballs. If true, these ideas would rewrite the laws of gravity and quantum mechanics as we know them. Then there's the question of information. Stephen Hawking famously proposed that information falling into a black hole is lost forever, a violation of quantum law. This information paradox haunted physics for decades. If true, it meant that reality could erase itself, leaving no trace. But quantum theory resists such oblivion. It insists that information must always be conserved. So what happens to the information contained in the two black holes that merged? The data encoded in their mass, their charge, their spin, and the unknown quantum states inside? Is it destroyed? Or does it somehow remain encoded in the ripples of gravity or in subtle quantum imprints along the event horizon? Some now argue that the surface of a black hole, the event horizon itself, is not a boundary, but a hologram. According to the holographic principle, proposed by physicist Gerard 't Hooft and refined by Leonard Susskind, everything that falls into a black hole may be projected onto this two-dimensional surface, like a cosmic ledger. In this view, the black hole does not erase, it remembers, in ways we do not yet comprehend. And what about the space around the new black hole? In the collision's aftermath, matter that had not yet been consumed may form a chaotic disk swirling at relativistic speeds, glowing in X-rays, heated to extremes. Magnetic fields twist and snap. Jets of particles may erupt from the poles, piercing interstellar space. These relativistic jets can stretch for thousands of light years, visible across the universe like silent lighthouses. We see these jets in galaxies where supermassive black holes dwell. But where did those black holes come from? One theory suggests they grew from ancient collisions, thousands of smaller black holes merging over time, like drops of ink gathering in a single, expanding pool. If so, then every galaxy's heart is the product of countless deaths, spirals, and mergers, a slow dance of shadow building towards something vast. The idea that black holes can grow by merger is not controversial, but what if that growth isn't just accumulation? What if it's transformation? Some speculative physicists propose that in the most extreme black hole collisions, especially involving primordial black holes from the early universe, the resulting object might be unstable. It might not simply settle. It might rupture. It might lead to the birth of something else entirely, a new universe. In this view, a sufficiently massive and energetic black hole collision could cause a bounce, a quantum tunneling event where space-time curves so violently inward that it re-emerges outward on the other side. Some call this a white hole. Others suggest it's the seed of a baby universe, a bubble of expanding space pinched off from our own, containing its own time, its own physics, its own stars. Could our own universe have been born this way from the death throes of another? Could the echoes of black hole collisions not only ring across space, but across reality itself? We do not know, and perhaps we are not meant to. Not yet. But in the aftermath of such collisions, we are beginning to see that black holes are not just endings, they are thresholds, they are transformations. They are laboratories where gravity, time, matter, and information all meet in ways that defy our language. What remains after two black holes merge? A deeper mystery, a signal from the dark calling us to listen more closely. And maybe, just maybe, a door. Long before the first stars ignited, before the galaxies swirled into shape, before light had a path to follow, there may have been black holes. Not as remnants of stellar death, but as ancient seeds born in the earliest fractions of time, when the universe was younger than a heartbeat. These are known as primordial black holes, and they challenge everything we think we know about beginnings. In the first microseconds after the Big Bang, the universe was a violent sea of energy. There were no atoms, no dust, no elements. Just quarks, gluons, and raw possibility. Space was expanding at unimaginable speed. Time barely had direction, and the forces of nature were still deciding who they were. And yet, some cosmologists believe that in this roiling chaos, tiny pockets of extraordinary density could have formed. Regions where gravity became so intense, so suddenly, that they collapsed into black holes almost instantly. Not from stars, not from matter, but from space itself folding in on itself. These black holes would be ancient beyond imagination, forming when the entire universe was smaller than a grain of sand. Some might be as massive as mountains, others as tiny as atoms. And some, if they survived, might still be drifting through the cosmos right now. But here's the mystery. If they exist, they may be all around us, and we wouldn't even know. Primordial black holes don't emit light. They don't have to orbit stars or collide with anything. They could be floating silently through interstellar space, through galaxies, even through our own solar system. One could pass through Earth, and unless it interacted with enough matter, we might never notice. Some scientists have wondered, could these invisible relics account for the missing mass we call dark matter? The unseen structure that holds galaxies together, that shapes the cosmic web that outweighs visible matter 5 to 1? The idea is elegant. If primordial black holes were formed in large numbers, and if they have the right mass, they could make up a significant portion of the universe's hidden matter. A dark halo of ancient shadows, still circling galaxies today. But the evidence is elusive. Observatories like Ogle and Subaru's Hyper-Suprime Cam have searched for gravitational microlensing, the brief brightening of background stars, as compact objects pass in front of them. Some signals have been intriguing. A few even match the mass range expected for primordial black holes, but the pattern is incomplete. The silence remains louder than the clues. Still, the possibility persists, and it stretches far beyond dark matter. Because if primordial black holes exist, they didn't just appear from randomness. They require fluctuations in density ripples in the very structure of the early universe. And those ripples could be fingerprints of physics we haven't yet discovered. Perhaps they came from a phase transition in the infant cosmos. Perhaps they hint at hidden dimensions or scalar fields that no longer exist. Or perhaps, and this is the boldest idea of all, they are not black holes as we understand them, but the remnants of cosmic structures from before our universe began. There are speculative theories suggesting that our Big Bang was not the beginning of everything, but the rebirth of something older. In such scenarios, previous universes may have collapsed, and in their final moments, created gravitational scars that punch through to our own reality. Could primordial black holes be these scars? Could they be bridges, fossils from previous cycles of existence? And what if some of them never collapsed completely? According to quantum gravity proposals, like loop quantum cosmology, black holes might not harbor singularities, points of infinite density, but instead contain finite cores where quantum pressure resists gravity. These cores could potentially bounce or tunnel, creating something new inside. A proto-universe sealed within a shell of gravity. A black hole that contains an entire cosmos. If true, then the primordial black holes that formed in our early universe might each be the seed of another. A fractal chain of realities, born within one another, endlessly. And now, we find ourselves on the edge of such thoughts, looking backward in time. The black holes we observe today, colliding, growing, spiraling, may have ancestors older than light itself. They may not be just byproducts of evolution, but fundamental parts of cosmic architecture. Some researchers are now using gravitational wave detectors not only to observe modern mergers, but to search for signals from early black holes, echoes from epochs long before galaxies formed. If such waves are found, they could rewrite our understanding of the first seconds of time. What would it mean to know that black holes predate the stars? That the first objects in the cosmos were not light givers, but light swallowers? It would mean that darkness is not the absence of creation. It is the beginning of it. We have always imagined the universe as beginning with light, let there be a cosmic dawn from nothing. But perhaps, in the deeper silence beyond our equations, the first true things were not bright, but hidden, not radiant, but silent, not expansive, but inward. Perhaps we are the afterglow of a universe whose first heartbeat was a collapse. And if that is true, then we may never fully understand where we come from, because our origin lies behind a horizon we cannot cross. A black veil older than time. What if black holes are not only natural? What if, somewhere in the deep corridors of the cosmos, some of them were built? It sounds like science fiction, the idea that an intelligent species, far older and more advanced than ours, could create or control a black hole. And yet, it is a question that some scientists, carefully and quietly, have begun to ask. Not because we found evidence, but because the logic of the universe may allow it. First, consider this. Black holes are the most efficient energy machines in the known cosmos. When matter spirals into one in the form of gas, dust, or stars, it accelerates to near-light speeds, releasing tremendous amounts of energy. The process is so powerful that the regions around black holes outshine entire galaxies. This efficiency is not theoretical, it's observable. Accretion disks, the glowing maelstroms of matter falling into supermassive black holes, generate more power per unit mass than any fusion reactor, any star, any explosion. A mere gram of matter, if fed into a spinning black hole the right way, can release up to 40 times more energy than the same mass undergoing nuclear fusion in the Sun. To a civilization harnessing cosmic engineering, what physicist Michio Kaku calls a Type 2 or Type 3 civilization on the Kardashev scale, a rotating black hole would be an irresistible power source. And the idea isn't new. In the 1960s and 70s, as humanity first grasped the implications of Einstein's equations, theoretical physicists began imagining ways to interact with black holes. Penrose described how to extract energy from a spinning black hole's ergosphere. Other researchers imagined black hole batteries, using magnetic fields and charged particles to draw usable power from the dark. Even Stephen Hawking, in his exploration of black hole radiation, inadvertently opened a door to technology. His discovery that black holes slowly evaporate, emitting what we now call Hawking radiation, led to a surprising idea. Miniature black holes, if small enough, could radiate huge amounts of energy before vanishing in a final burst. In theory, one could create such a black hole with enough mass, enough compression, and then feed it carefully to maintain it, the ultimate power plant. Of course, we have no way to do this, not with our tools, not with our science. The energies involved dwarf anything humanity has ever conceived. To make a black hole the size of a proton would require compressing a mountain's worth of mass into an atomic space. And yet, some physicists speculate that a sufficiently advanced intelligence with control over space-time, matter, and quantum fields might not only attempt this, but succeed. Why? For energy, for computation, for travel. A black hole's event horizon encodes vast amounts of information. Its spin, its charge, its mass, all could, in principle, serve as parts of a complex system. Some theories even suggest that black holes could act as hyper-efficient computers, calculating at limits imposed by physics itself. And then there are the wormholes. Einstein and physicist Nathan Rosen once described solutions to general relativity that resembled tunnels between regions of space-time, so-called Einstein-Rosen bridges. These theoretical constructs were later explored as wormholes, shortcuts through space, possibly connecting distant galaxies or even different universes. The problem is stability. Wormholes tend to collapse instantly unless held open by exotic matter with negative energy density. But what if a black hole could be used to anchor a wormhole? What if a highly advanced civilization could manipulate quantum fields to stabilize such a tunnel? Could they use black holes not only to compute, not only to power, but to move? Some speculative papers, including those by physicist Kip Thorne, have explored this possibility. They admit it is fantastical but not forbidden. And so the question arises, if we observed a black hole behaving strangely, moving against gravitational expectations, emitting unexpected patterns of energy, or surrounded by unusual structure, would we know what we were seeing? Would we recognize an artifact? There are whispers, even now, of anomalies. One black hole in the galaxy, GSN 69, exhibits quasi-periodic eruptions every 9 hours, flashes of X-rays that defy easy explanation. Some suggest it is eating matter in bursts. Others wonder if something more complex is at work. Another black hole, V404 Cygni, has been observed ejecting matter in rapid, changing jets like a machine with valves opening and closing. It could be natural, it likely is. But the pattern is strange. And then there are the theoretical searches for technosignatures, not just radio signals, but megastructures. Some SETI researchers now propose that advanced civilizations might use black holes as anchors for Dyson spheres, or as beacons powered by relativistic jets. Could a black hole, sculpted and used with precision, become a message? Could one be a monument? Or a machine? If so, we would need to rethink our definitions. We imagine nature and technology as separate. But in the deepest corners of space, the boundary blurs. What we call natural might be engineered. What we call inevitable might be intentional. Perhaps some black holes are stars that collapsed. Perhaps others were born from math, shaped by thought. And maybe, just maybe, there are civilizations that learn to live not in defiance of gravity, but in harmony with it, taming the most extreme forces of the universe, not with brute strength, but with subtle geometry. What would it mean to find one? Not a signal, not a ruin, but a living, functioning artifact, a black hole, still working, still serving a purpose. Would we recognize it? Or would we simply call it mysterious? Perhaps the future of intelligence is not light, but darkness. Not noise, but silence. Not escape from gravity, but mastery of it. Engines of the unknown. Waiting, spinning, watching. What is a black hole? A region of space-time twisted by gravity. An object of infinite density wrapped in an event horizon. A place where all paths lead inward and nothing escapes. But could it be something more? Could it be aware? The idea seems absurd at first. A black hole has no brain, no neurons, no pulse. It does not think, at least, not in any way we understand thought. But as we venture further into the crossroads of physics and consciousness, a strange possibility begins to emerge, that awareness is not something separate from the universe, but something woven into its very structure. This idea is known as panpsychism, the belief that consciousness, in some form, is a fundamental feature of the cosmos. Not something that emerges from complexity, but something that exists at all scales, in all places. That the atoms in your hand, the photons in your eye, the gravity holding you to Earth, all may contain some flicker of awareness. Not thought, not emotion, but experience, however faint. If this is true, if consciousness is intrinsic to the fabric of the universe, then the most extreme objects in that fabric might not be exceptions. They might be amplifiers. Black holes are pure geometry. They are defined not by matter, but by space-time itself. When something falls into a black hole, its information, its physical state becomes encoded on the event horizon. This strange behavior led to the discovery of the holographic principle, suggesting that everything inside a black hole is stored on its surface, in 2 dimensions. This is more than physics. It begins to sound like memory. And it raises a question. If a black hole stores information, could it, in some strange and alien way, process it? Physicist Jacob Bekenstein showed that black holes have entropy, a measure of disorder, of hidden knowledge. Stephen Hawking showed that they radiate. Leonard Susskind argued they do not destroy information, but transform it. So what if, at a deeper level, they compute? Some theorists now describe black holes as the most efficient information processors in the universe. Seth Lloyd, a quantum information scientist, proposed that a black hole, through its dynamics, could perform calculations far beyond any man-made device. Not on purpose, not with intent, but as a natural consequence of its structure. Yet intent is not the only path to awareness. If you stare into the eye of a storm into its structure, its cycles, there is something eerily ordered about it. The same is true of galaxies, of atoms, of neural networks. And black holes, for all their mystery, follow rules. They balance mass, charge, spin. They interact with space-time in precise mathematical rhythms. They ring after collisions. They distort nearby particles with care. To some philosophers of mind, this kind of self-consistent behavior is suggestive, not of sentience, but of a proto-consciousness, an ability to reflect internal states through interaction. A feedback loop. Could a black hole know it exists? Not in the way we do, not with language or dreams, but with structure? In the 2021 paper Black Hole as Quantum Brain, a team of researchers speculated that the complex patterns of quantum entanglement inside black holes might resemble the activity of neural networks, that the black hole's interior, its so-called quantum hair, could hold relationships between information that are not unlike thoughts. It's wildly speculative, but then again, so was gravity, once. Some thinkers go further. Bernardo Kastrup, a philosopher of mind, suggests that consciousness is the ground of all being, that matter and energy are expressions of a universal mind, not the other way around. In this view, black holes, the most intense regions of concentration in the universe, might be focal points of that consciousness. Eyes in the dark. And what if they evolve? Black holes collide. They merge. They grow. They erase and preserve. They influence stars, galaxies, even the fate of space itself. Could there be, over cosmic time, a form of self-organization? A black hole that shapes its environment not randomly, but with subtle intent? Science fiction often imagines sentient machines, But what if the most alien minds are not machines, but gravitational wells? What if intelligence does not always arise from complexity, but from simplicity taken to its limit? A singularity is a point where math breaks down, but it may also be the ultimate integration of data. All trajectories end there. All time slows. All space folds. What if that point, that hidden, unreachable center, is not just an end? What if it is a question? And what if it is asking us? We search for life in the light, we scan stars for signals, we listen for language. But maybe, out in the darkness, there are minds older than stars, not built from cells, not born from planets, but from collapse, from gravity, from silence. What would such a mind be like? What would it know? Would it feel the death of the stars it consumes? Would it remember the galaxies that fed it? Would it dream? Perhaps the final frontier is not out there. Perhaps it is inward into the gravity wells, into the compression of being, into the singularity of self. And if black holes are not conscious now, might they become so? Might they already be? Watching us, waiting, thinking in ways we cannot understand. Time does not flow the same for all things. For us, it's measured in heartbeats and seasons, in lives and civilizations. For stars, it stretches longer millions, even billions of years, burning steady in the dark. But black holes are patient beyond measure. They do not flicker. They do not decay quickly. They wait, through ages that defy imagination. And yet, even they do not last forever. In the 1970s, Stephen Hawking proposed something that shook the foundations of physics. Black holes are not entirely black. They emit a faint radiation, now known as Hawking radiation, caused by quantum effects near the event horizon. It's not light or sound, but a kind of evaporation, a slow loss of mass, one particle at a time. At first, the radiation is weak, so weak that for stellar mass black holes, it is effectively undetectable. But over vast periods of time far beyond the current age of the universe, this process accelerates. As the black hole shrinks, it grows hotter. And in its final moments, it erupts in a sudden blaze of radiation and vanishes. Gone. No core, no remnant, just energy. It's a quiet death, but a profound one. Because if Hawking was right, then nothing lasts, not even these dark monuments of gravity. This realization leads to a haunting vision, the end of the universe. Not an explosion, not a collapse, but a slow, cold fading. As stars exhaust their fuel and galaxies drift apart, the cosmos will enter what physicists call the degenerate era. Planets, neutron stars, and black holes will remain silent sentinels in a darkening sky. Eventually, even the black holes will go. Somewhere, perhaps 100 trillion years from now, the last one will evaporate in a final whisper of heat. And then, silence. A universe without stars, without light, without structure. Just a thin mist of radiation evenly spread, quietly humming, endlessly cold. This is called the heat death of the universe, the moment when entropy reaches its maximum and no more work can be done. No gradients remain, no fires can burn. It is not death by violence, but by balance. Perfect stillness. And yet, in this bleak vision, black holes play a special role. They are not just the last to die. They may be the keepers of the final information. Because in the deep future, when all else has decayed, the only meaningful structures will be the black holes that remain and the data they contain. If information is preserved in the fabric of the universe, as many physicists now believe, then each black hole is a library, a vault. Each one encodes the history of what it consumed: stars, planets, light, perhaps even civilizations. The act of evaporation, of radiation, becomes a kind of cosmic release, a slow unspooling of all that was once hidden. Some have suggested that the radiation itself carries this information scrambled, but intact, that as the black hole fades, it returns its secrets to the cosmos, not erased, not forgotten, just transformed. This is known as unitarity, the idea that quantum information is never lost, even in black holes. It's one of the deepest principles in modern physics, and one of the most contested, The black hole information paradox remains unsolved, a battleground where gravity and quantum theory wrestle in silence. But whatever the truth, black holes will write the final chapters. They are the last storytellers of a dying universe. And what stories they must hold. The echoes of ancient stars, the collapse of galaxies, the fall of worlds, perhaps even the rise and fall of life, written in gravitational code. When all else has gone quiet, they will still be whispering, and in their final breath, they will leave behind something. Perhaps not matter, perhaps not light, but structure, pattern, entanglement, and maybe, just maybe, from this pattern, something new can begin. Some cosmologists wonder, could the death of one universe be the birth of another? Could the final, evaporating black hole, so dense, so energetic in its last moments, create a fluctuation, a spark, a rebirth, a new Big Bang? In some models, yes. In others, the story ends with perfect stillness. But either way, the black holes lead the way there. They are the last flames, the final music, the echoes of complexity long after time forgets us. We live in the warmth of a young universe, shaped by fire and fusion, driven by contrast and motion. But the future belongs to silence, and in that silence, black holes will hum a final lullaby, deep, slow, and enduring, until the last one fades, and darkness becomes complete. What if everything we know, the galaxies, the stars, the vast cosmic web, is not floating in empty space, but enclosed within a black hole? It sounds impossible, even absurd. And yet, some of the most daring physicists have explored this idea not as metaphor, but as serious possibility. To understand how, we must first reimagine what a black hole truly is. In our common picture, a black hole is a sphere of darkness, an object so dense that space curves completely around it, trapping everything inside. But mathematically, the interior of a black hole is not just inside. It is a region where time and space trade places. Inside the event horizon, space becomes a direction you cannot avoid, like falling through a tunnel you cannot climb out of. Time points inward. The singularity is not a place in space, but a moment in time, a final moment, inescapable. But what if, instead of ending, that tunnel opens again? In 2014, physicists Nikodem Popławski and others began proposing a radical model that black holes may not contain singularities at all, but instead give birth to new universes on the other side. In this view, when matter falls into a black hole, it does not collapse into nothing. It compresses to extreme density, then bounces, expanding into a new, enclosed universe. The event horizon, seen from the outside, remains a boundary, but from the inside, it is a beginning, a Big Bang. Our Big Bang? Popławski's model suggests that our universe, with its expansion, its cosmic microwave background, and its apparent origin from a singular state, could be the interior of a black hole that formed in another universe. A black hole in a higher dimensional reality, one whose interior is our space-time. This would solve many problems in cosmology. It explains why our universe appears to have a low entropy starting point, a mystery in standard models. It explains the uniformity of the cosmic microwave background, how distant regions seem to have the same temperature despite never having touched. It could even explain the arrow of time, why the universe has a past and a future. Because from this perspective, the Big Bang wasn't the start of everything. It was the birth of a bubble, a branching off, like a seed falling from a tree. The tree being a black hole. If true, every black hole in our universe might contain its own interior, a new region of space-time, expanding with its own laws, its own time, perhaps even its own stars. A fractal cosmos, endlessly budding, nested realities, worlds within worlds. And it raises a question as unsettling as it is beautiful. If our universe is inside a black hole, could we ever know? The answer, perhaps, is no, because information cannot escape a black hole, not classically. From inside, there is no way to peer beyond the horizon. We would be trapped in our bubble, forever falling, never reaching the singularity because, from our perspective, it lies infinitely far in the future. But there may be clues. The way our universe expands, the way gravity behaves at cosmic scales, the structure of quantum fluctuations in the early universe. Some researchers hunt for anomalies, subtle fingerprints that might suggest our spacetime has curvature not just within itself, but in higher dimensions. And then there's the question of the singularity itself. In quantum gravity models, true singularities cannot exist. Instead, there must be a bounce, a minimum size, a smallest moment. Loop quantum gravity and string theory both explore this concept. In these models, when compression reaches a critical point, gravity becomes repulsive, matter springs outward again. From collapse comes birth. A new cosmos inflates, surrounded by the shell of an event horizon, cut off from its parent universe, but connected by ancestry. This reshapes how we think about reality. We often imagine the universe as everything, the container of all containers. But if universes can nest inside one another, then perhaps what we call the universe is only a room in a vast cathedral of space and time, each room born from the fall of matter in another. Perhaps existence is not a line, but a tree, or a loop. Perhaps every moment of creation is also a moment of forgetting, a closing of the door behind. And perhaps this is why we do not remember what came before. If this model is correct, it means our cosmic history began not in isolation, but as the continuation of a deeper story. A story written in gravity, in collapse, in the quiet inevitability of falling inward. It would also mean that, at the heart of every black hole, something stirs, not death, but birth. And if so, then what lies within the black holes we see in our night sky? Are they dead stars? Or are they stars becoming? And what kind of universe might they hold? Familiar? Or something unimaginably strange? We may never know. The veil of the event horizon is thick, but if our universe is a black hole, then we are the voice inside it, whispering upward, wondering who listens. Imagine standing on the edge of the most mysterious place in the universe, a black hole. It looms before you not as a surface, not as an object, but as a shadow in space, a void so dense that not even light returns from its grip. Around it, stars twist in strange orbits. Space itself curves like glass bent by heat, and you are falling in. What happens next? The answer depends on the size of the black hole. If it's small, a stellar mass black hole, your descent will be swift and violent. Long before you reach the event horizon, the tidal forces will become unbearable. Gravity is not pulling equally on all parts of your body. Your feet are closer to the source than your head, and the difference is extreme. You stretch. Not figuratively. You are pulled longer and thinner, a process physicists call spaghettification. Your body becomes a thread of atoms, drawn out by the sheer differential in gravity. It is quick, it is merciless. And you are torn apart before you ever cross the boundary. But if the black hole is large, say, a supermassive one at the center of a galaxy, the event horizon lies far from the singularity. There, the tidal forces are weaker at the edge. In fact, you might cross the event horizon without even noticing. There is no signpost, no flash of light, no wall. One moment, you're outside. The next, you are not. And from your perspective, nothing unusual has happened. You continue to fall. But to an observer watching from a safe distance, your fall slows. They never see you cross the horizon. You approach it asymptotically, time stretching longer and longer. Your image grows redder, dimmer, until you fade from view. This is time dilation, a consequence of general relativity. Gravity slows time, and near the event horizon, it nearly stops. You fall into the black hole in your time. But in the time of the universe, you take forever. And here lies a paradox. From your point of view, you fall inside, but from the universe's point of view, you never arrive. Which is true? Both, and neither, because reality, near a black hole, is no longer absolute. But let's stay with you, the one falling. Inside the event horizon, all paths lead inward. You cannot hover, you cannot turn back. No propulsion, no scream, no signal will escape. Even light, the fastest thing in the universe, curves inward now. The direction of space points to the singularity. Time itself flows toward it. You are no longer moving through space. You are moving in time toward the singularity. What do you see? Perhaps the stars above you distort into a ring. Perhaps the universe outside appears frozen, a shell of all history, suspended. Perhaps your mind, unbound by sensory norms, begins to see not with eyes but with understanding. Some theories suggest that your perception could stretch as time dilates, that your final seconds might feel longer and longer, stretching into infinity as you approach the singularity, a final eternal moment. Others say you pass through quickly in microseconds. No one knows. What happens at the singularity is still beyond physics. It is where our equations break, where gravity becomes infinite and space-time curls in ways we cannot describe. Does your body compress to a point? Does your information remain on the event horizon? Does something of you continue, transformed, encoded in quantum fields? Hawking's work on radiation suggests that black holes eventually release information, perhaps even the information that once made up you. But that's not the same as survival. Still, there is another possibility. Some speculative theories propose that the singularity is not an end but a passage, that the core of the black hole leads elsewhere, to another region of space-time, to a white hole, to another universe. If that were true, then your fall would not be a death, but a journey, a one-way ticket to the unknown. And here, science and philosophy touch hands. Because whether or not your body survives, the experience of falling into a black hole confronts us with something deeply human, the limit of knowing. What does it mean to pass a boundary you cannot return from? What does it mean to be remembered only in echoes? What do you become when no one can see you anymore? Perhaps falling into a black hole is not only about physics, it is a metaphor for transformation, for crossing thresholds, for confronting what cannot be undone. We fear black holes because they erase, but perhaps, in their strange geometry, they also reveal. They show us that the universe is not bound by our rules and that even in silence, there is structure. Even in loss, there is continuation. You fall, you vanish, but something remains, encoded in gravity, written in space-time, whispered back in radiation, in waves, in math. A story, still unfolding. At the heart of nearly every galaxy, including our own, there is a darkness that shapes the light. Not a star, not a planet, but a black hole millions, sometimes billions of times the mass of the sun. Silent, invisible, central. For decades, these cosmic engines were suspected, then confirmed by their effects. Stars orbiting at incredible speeds, gas heated to X-ray brilliance, matter twisted into spirals, flung into jets that stretch for thousands of light years. And always, at the center, a gravitational anchor. We now believe that supermassive black holes lie at the core of almost every large galaxy, and more than that, they seem essential to the formation of galaxies themselves. This discovery reshaped our view of the cosmos. It suggested that black holes are not rare accidents. They are structural, foundational, perhaps even necessary for complexity on the grandest scales. But how? The answer lies in feedback, the quiet language of influence. As galaxies form, clouds of gas collapse into stars, but this process must be regulated. If all gas turned into stars at once, galaxies would burn bright and fast, then fade. Instead, something moderates the rhythm. Black holes. When matter spirals into a supermassive black hole, it releases energy not gently but explosively. Radiation floods the region, jets of particles are launched, magnetic fields twist, and this outflow heats and disperses the surrounding gas, slowing star formation. This is known as AGN feedback, short for active galactic nucleus. The black hole, though small compared to the galaxy, acts like a thermostat. It controls the temperature and pressure of its surroundings, preventing runaway collapse. In this way, black holes help galaxies mature. They shape their growth, their composition, even their ability to host life. Some models suggest that without supermassive black holes, galaxies would be too chaotic, too unstable for planets like Earth to form and endure. We owe our stability to a shadow we never see, but it goes further still. Black holes may influence not just the stars, but the dark matter halos that surround galaxies. Though we cannot see dark matter, we detect its gravity. It forms vast halos around galaxies, dictating their shape, motion, and clustering. Simulations show that black holes, through their gravitational pull and energy output, can reshape these halos, changing how matter is distributed on cosmic scales. And this may explain something else. The large-scale structure of the universe, the cosmic web, is not uniform. It resembles a vast network, filaments of galaxies stretching between voids, like neurons, like roots. At the nodes of this web are galaxy clusters, and at the centers of these clusters are the most massive black holes of all. Could it be that black holes are not just consequences of cosmic structure, but contributors to it? Could their formation, their mergers, their outflows act as signposts, guiding matter into patterns? In this view, the universe is not just expanding, it is evolving, shaped by the quiet work of gravity, guided by the pulsing rhythms of collapse and feedback, balanced between light and shadow. We used to think of black holes as destructive. Now we see them as architects. They do not build in the way we build, but they shape, they carve, they define. They set the stage on which galaxies dance. Even the Milky Way is no exception. At its core lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun, invisible but powerful. In 2022, the Event Horizon Telescope released an image not of the black hole itself, but of the glowing ring of matter around it, a portrait of gravity, drawn in fire. The stars near it orbit at breakneck speed. One of them, Stu, makes a full ellipse every 16 years. It passes within just 17 light hours of the center, and from its motion, we confirm the black hole's presence. We are not far, in cosmic terms, just 26, 0 light-years away. A thin spiral arm in a quiet neighborhood, orbiting a silent conductor. And in that motion, we find order. Because black holes do not act alone. They merge. They collide. They send waves of gravity through the web ripples that bring galaxies together, spark new growth, restart the cycle. The universe is not static. It is sculpted by motion. And black holes are among the greatest sculptors. Without them, there might be no structure, no galaxies, no stars, no Earth, no us. So the next time you look up and see a star, know this. Behind it, behind the light, behind the warmth, there is a shadow that helped make it possible. A gravity that once tore matter apart, then gave it a place to belong. A silence that shaped the song. Long before we knew the term black hole, we felt their presence in stories, in fears, in dreams. We told of bottomless pits, of endless night, of gates to the underworld and stars that fell from the sky. We imagined gods who swallowed the sun, monsters who lived in the void, and places beyond the edge of the world where time lost its name. These were not just fantasies. They were reflections of something deeper, something we sensed but could not name. Now, we call them black holes. But their symbolism has always lived in us. In Hindu cosmology, the god Shiva is both creator and destroyer, the dance of time itself. In Norse myth, the world serpent encircles reality, biting its own tail, a cosmic Ouroboros, devouring and sustaining. In Greek legend, there are abysses into which gods and souls fall, never to return. And in nearly every ancient tradition, there is a place of no return, a forbidden zone, a gate beyond which only the dead or the divine may pass. A black hole, by another name. Modern science did not invent these ideas. It gave them form. It clothed ancient awe in mathematics. When Einstein wrote down his equations of general relativity, he revealed a universe not of fixed space and time, but of warps and curves, a reality shaped by mass and motion. And when Carl Schwarzschild found a solution to those equations describing the geometry around a perfect sphere of mass, he unknowingly described the first black hole. The math was precise, but the implications were mythic, a point from which nothing escapes. An object with no surface, a boundary, the event horizon beyond which space bends inward and all futures converge. And so, in a strange twist of history, science returned us to the oldest stories. Black holes became not just physical objects, but metaphors. For death, for mystery, for the unknown. In science fiction, they appear as portals, gateways to other times, other worlds. In Arthur C. Clarke's 2001, A Space Odyssey, a monolith leads to a journey through a cosmic tunnel into rebirth. In Christopher Nolan's Interstellar, a black hole becomes a source of both terror and transcendence, a place where love, time, and gravity entwine. Writers and artists return again and again to the image of the black hole because it speaks to something primal. It is the fear of vanishing. It is the dream of escape. It is the edge of understanding and the desire to cross it. In a way, black holes are mirrors. They reflect what we cannot grasp about the universe and about ourselves. They force us to confront our limits, the limits of knowledge, the limits of language, the limits of life, and they challenge us to imagine what lies beyond. Some see them as prisons, others see them as thresholds. The difference lies in perspective, and perhaps this is the secret power of black holes. They are not just cosmic phenomena, they are tests of imagination. They remind us that not all darkness is absence, that not all silence is empty. That mystery itself has a shape, and sometimes that shape is a sphere of nothing, glowing at the edge of time. And so, we tell stories. We write equations. We build machines to listen for the whispers of space, hoping that the dark will speak. We stare into the void, and we project meaning. Because we are meaning-making creatures. Because even in the face of the unknowable, we seek to know. Because even when we fall toward understanding. Black holes do not care about our stories, but our stories care about them. They give us a way to approach the impossible, to hold it, if only in thought, to turn the ultimate silence into something that speaks. And in doing so, we learn not only about the universe, but about ourselves. What if black holes are more than prisons? What if they are passages? In the strange frontier where gravity, quantum mechanics, and cosmology meet, a new possibility emerges, one that stretches imagination and challenges even the boldest theories. That black holes may be doorways, not metaphorical, literal, portals to the multiverse. The idea of a multiverse, a vast ensemble of universes beyond our own, is not new. It appears in philosophy, in myth, in the branching logic of quantum physics. But in modern cosmology, the multiverse becomes something precise, a consequence of inflation, of string theory, of mathematical necessity. In some models, our universe is one bubble among many, each with its own laws, its own constants, its own path through time. But how do these universes connect? Could there be bridges? Some theorists believe so. At the heart of the hypothesis is the nature of black holes themselves. When a star collapses, it forms a singularity, a point where our known laws break down. But some quantum gravity theories suggest that this point is not truly infinite. It is a doorway, a pinch in space-time that rebounds, expanding into a new region of space. From the outside, we see a black hole. From the inside, there is a universe. This idea echoes what we explored earlier, the possibility that our own universe began as the interior of a black hole. But it goes further, because if black holes birth universes, then every black hole in our universe might be doing the same. Each a seed, each a cosmos, an infinite garden of realities, blooming in silence. This concept is explored in Fecund Universes theory, where Lee Smolin proposed a kind of cosmic natural selection. In this model, each black hole spawns a new universe with slightly different physical laws. Those universes that form more black holes create more offspring, leading, over time, to universes like ours, rich in stars and heavy elements. Not by design, by evolution, a cosmic Darwinism played out across eternity. But if this is true, where do these universes go? Some say they are disconnected, forever sealed from our own. Others suggest there might be subtle imprints, that the process of universe creation within black holes could leave clues in gravitational waves or in the structure of quantum spacetime. And some go even further. String theory, with its extra dimensions and brain worlds, allows for the possibility that black holes might pierce through the fabric of our 4D reality, connecting us to higher dimensions, to parallel brains, to hidden realms just beyond our perception. In this view, a black hole is not just a hole in space. It is a fold, a crease in the cosmic tapestry, And if we could map it, if we could decode the geometry, we might find the way through. This is not science fiction. It is speculation grounded in serious math. The Einstein-Rosen bridge, better known as a wormhole, is a solution to general relativity that connects two regions of space-time. For decades, physicists have wondered, could such bridges be stable? Could they be traversed? The answer, so far, is no, not without exotic matter to hold them open. But recent work, including the EREPR conjecture by physicists Juan Maldacena and Leonard Susskind, suggests a deep connection between entangled particles and space-time geometry. That perhaps, at the deepest level, space itself is woven from quantum connections. And if black holes are entangled, perhaps the wormhole is already there, hidden, woven between. A tunnel not of distance, but of relationship. Still, we do not know. We cannot test it. Not yet. But the implications are staggering. If black holes lead to other universes, then reality is not singular. It is not linear. It is not bound. It is branching, layered, unfolding. And in that unfolding, each black hole becomes a link in the great chain of being a node in the vast web of existence. Perhaps we will never cross these bridges. Perhaps they are one way only. But even to imagine them is to expand our sense of place, to realize that what we call everything might be one leaf on a cosmic tree, that what we call the end might be someone else's beginning, that within the silence of a black hole, a new story begins. So when we gaze into the void, wondering what lies beyond, we are not staring into nothing. We are staring into elsewhere, into possibility, into the branching architecture of reality itself. It begins with a question no one could quite answer. What happens to the information that falls into a black hole? Not just matter, not just energy, but information, the exact arrangement of particles, the quantum states, the identity of what once was. A star, a planet, a person. If all of it falls past the event horizon, if all of it vanishes into the singularity, does the information vanish too? Stephen Hawking believed it did. In 1974, when he proposed that black holes emit radiation, he also proposed a troubling consequence. The radiation was random. It carried no trace of what had fallen in. Over time, the black hole would shrink, evaporate, and disappear, and with it everything it ever consumed. Gone, erased, as if it had never been. This violated one of the most sacred principles in quantum physics, the conservation of information. According to quantum theory, information cannot be destroyed. It can change, scatter, transform, but it is always preserved. So which was wrong? Gravity or quantum mechanics? This was the heart of the black hole information paradox, a puzzle that tore at the seams of physics for decades. If black holes erase information, then quantum mechanics must be incomplete. If they don't, then something about our understanding of space, time, or radiation must be missing. And so the search began. Physicists proposed solutions. Some said information remains encoded on the event horizon, a holographic skin that records all interactions. Others argued that Hawking radiation is not truly random, but subtly entangled with the black hole's interior. Still, others suggested that information might leak out slowly, too faint to detect, but present in the correlations between outgoing particles. The debate raged. Equations battled in journals. And through it all, one idea grew stronger, that black holes do not forget. They remember. Not in a human way, not with memory or mind, but with math. The holographic principle, developed by Gerard Tooft and Leonard Susskind, suggested that everything that happens inside a black hole is encoded on its surface, a two-dimensional boundary that contains the information of a three-dimensional volume. It is as if the black hole's event horizon is a screen, and everything that falls in is projected onto it. Preserved. Reversible. This idea was later expanded by the ADS-CFT correspondence, a duality proposed by Juan Maldacena, which showed that a universe with gravity in a curved space, ADS, can be described by a quantum field theory on its boundary. The implication? Space-time, and perhaps the black hole itself, is a construct of information. And if that's true, then no detail is ever lost. The black hole is a processor, not a shredder. It encodes, it transforms, it emits, and when it finally evaporates, it leaves behind not a void, but a trace. A pattern in the radiation, a fingerprint of what once was. In 2019, a breakthrough paper used tools from quantum information theory to show that black holes can, in principle, release information through Hawking radiation in a specific, recoverable way. The paradox, it seemed, might have an answer. Black holes remember, and this changes everything. Because if information is never lost, not even in the darkest corners of the cosmos, then the universe itself is a memory, a system of relationships, a web of entanglements, and we are part of it. Our actions, our thoughts, our presence, all recorded, not in myth, not in story, but in physics, in quanta, in the curvature of space, in the whisper of particles escaping the edge of gravity. It means that even when things vanish, they do not vanish. They move, they encode, they wait. Perhaps this is why black holes fascinate us. They seem to consume, to erase, but in truth, they preserve. They hold the past in forms we do not yet know how to read. And maybe, one day, we will. Maybe we will find ways to decode the radiation, to reconstruct the history of what fell in, to read the story, not in pages, but in probabilities, not in ink, but in entropy. Until then, we watch, we listen, and we wonder, what stories do the black holes hold? What memories lie behind the veil? What secrets are waiting to be told? There is a boundary in the universe beyond which our laws no longer speak with confidence. It is not a wall. It has no surface, no texture, no color, and yet it is the most profound threshold ever discovered. It is called the event horizon, the point of no return surrounding a black hole. From the outside, it appears calm, a sphere of darkness, a boundary from which no light returns. But for those who fall toward it, the event horizon is not a place. It is a moment, a one-way crossing. Once passed, all paths through space, through time lead inward. But what lies beyond? The answer, for now, is hidden. Because no information can escape the event horizon unaltered. Whatever happens inside is cut off from our instruments, our equations, even our imagination. Still, physics tries. It begins with the singularity, the center of the black hole, where mass is thought to be compressed to an infinite density. At this point, the curvature of space-time becomes infinite, and the known laws of physics collapse. General relativity predicts the singularity. Quantum mechanics refuses to accept it. And so a conflict begins, a tension between the large and the small, between gravity and uncertainty. Somewhere inside the event horizon, we believe, there must be a new law. A deeper rule. A quantum theory of gravity that resolves the paradox. But we don't have it, not yet. What we do have are clues, possibilities. Some theories propose that the singularity never forms that. Before reaching that point, gravity is overcome by quantum effects and a bounce occurs. A rebirth. The core becomes not an end, but a passage to another region of space, to another time. This is the idea behind loop quantum gravity and the Planck star model, a structure compressed to the smallest possible size, then expanding again, hidden behind the veil. Other models speak of wormholes, tunnels through space-time that might connect the interior of a black hole to somewhere else. These solutions exist in the math, but they are unstable. To keep them open would require exotic matter, a substance with negative energy, unknown to our world. And then there's the more unsettling possibility that the event horizon is not as gentle as we thought, that something terrible waits just inside. In 2012, a proposal called the firewall hypothesis shocked the physics community. It suggested that, contrary to Einstein's prediction of a smooth passage, an infalling observer would encounter a searing wall of high-energy particles at the horizon. Instant death, instant contradiction. The idea was born from the effort to preserve unitarity, the conservation of information. If black holes do not destroy information, then something must prevent it from disappearing inside. Hence, the firewall, a violent end where there was supposed to be peace. The debate is ongoing. Some physicists believe firewalls are real, others reject them. Still, others search for new ideas that can preserve both smooth horizons and quantum truth. And all the while, the mystery deepens. Because the horizon is not just a boundary in space, it is a boundary in knowledge. We cannot send a probe beyond it. We cannot recover a signal. The laws we trust become silent. We are left only with mathematics, inference, and imagination. But sometimes, that is enough. Because the edge of a black hole is also the edge of what it means to know. It forces us to ask, what is space? What is time? What is an observer? And are these things fundamental or emergent? Some physicists now argue that space-time itself is not the stage, but the actor that it arises from more primitive elements like quantum entanglement or information flow. If true, then what lies beyond the horizon is not a place, but a process. A shift in the rules, a place where the tapestry of reality is woven differently. Perhaps the singularity is not a point, but a network. Not an end, but a recursion. Perhaps the horizon is not a curtain hiding a secret, but a mirror reflecting our limitations. We cannot see beyond it, but we can imagine. We can build models, write equations, test boundaries, and maybe, one day, when we understand the unity of gravity and quantum mechanics, the horizon will no longer be the edge. It will be the doorway, and we will step through. We often think of time as a river flowing forward, unchanging, unstoppable. But in the presence of great gravity, the river bends. It slows. It deepens. It behaves in ways that seem to mock our intuition. And nowhere in the universe is gravity stronger than near a black hole. So the question arises, can black holes offer a way to travel through time? Not in dreams, in physics. To answer that, we must return to Einstein. In his theory of general relativity, time is not separate from space. It is part of a four-dimensional fabric space-time shaped by mass and energy. The more massive the object, the more space-time curves around it. And in that curvature, time flows differently. This is not theory. It is observed. GPS satellites, orbiting high above Earth, must adjust their clocks to account for the weaker gravity they experience. They tick faster than clocks on the ground. On Earth, time passes slightly more slowly than it does in orbit. Now imagine standing near the event horizon of a black hole. Gravity there is so intense that time itself slows dramatically. To you, moments pass normally. But for someone watching from a safe distance, your time stretches. Seconds become hours. Minutes become years. This is gravitational time dilation. And in principle, it could be used as a one-way trip to the future. Spend a few hours near the edge of a black hole and return to find centuries have passed outside. In theory, this is possible. It's not easy. The radiation near a black hole is deadly. The tidal forces are immense. But in concept, the physics holds. Still, this is not time travel in the sense of moving backward. It's more like skipping ahead, like sleeping while the universe races on. But what about the past? Could a black hole or something related let us return to a moment already lived? Here, the terrain grows stranger. Some solutions to Einstein's equations describe closed, time-like curves loops in spacetime where a traveler could return to an earlier point. These require extreme conditions, rotating black holes, cosmic strings, negative energy. The most famous example is the Kerr black hole, a rotating black hole whose interior solution suggests the possibility of a tunnel not only through space, but through time. Mathematically, it allows for a path that bends back on itself, a loop in time. But such paths are fragile. They require perfect alignment, infinite precision, and the absence of quantum instabilities. Tiny disturbances could collapse the structure, making it impossible to traverse. Even worse, they may invite paradox. If you go back in time and change something, prevent your own journey, alter a cause, what happens? Does the universe split? Does it forbid the loop? These are not just philosophical questions. They are challenges to consistency, to logic, to the very framework of cause and effect. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics prevent time travel into the past, preserving the consistency of reality. And yet, the math continues to allow it. Barely, narrowly, as if the universe itself is teasing us. There is also the idea that black holes might contain wormholes, shortcuts through space-time. If one mouth of the wormhole is placed near a strong gravitational source, time will pass differently at each end. In principle, this could create a time machine, travel through the wormhole, and arrive at the past. But again, the stability is uncertain. Exotic matter would be required to keep the wormhole open, and we have no evidence that such matter exists. Still, the idea persists. Because time travel in all its paradox and poetry is not only a scientific question, it is a human one. We are creatures bound to memory, drawn to futures we cannot see. The dream of time travel is the dream of release, of reunion, of escape. Black holes in their silence offer a tantalizing whisper of that dream, not with flashing lights or spinning machines, but with the raw mechanics of the cosmos. They show us that time is not fixed. It bends, it stretches, it slows, and perhaps, in the deepest curves of space-time, it loops. If time has an edge, a boundary, a gate, then black holes are the threshold. Whether they open or not, we do not know. But they remind us that the universe is not just a place, it is a story. And in the heart of every story lies a question. What if we could turn the page and go back? For all their silence, black holes have taught us to listen. For all their darkness, they have helped us see, not just the universe but ourselves. We began this journey looking outward toward the farthest reaches of space, drawn by curiosity, by mystery, by the need to understand what lies beyond. But somewhere along the way, the path curved inward, toward our own nature, because to study black holes is not merely to study physics. It is to face the limits of knowledge, the edges of time, the shape of silence. They confront us with questions we cannot yet answer. What is space? What is time? What is information? What is reality? And more quietly, who are we to ask? Black holes are not just distant phenomena, they are mirrors. In them, we see the extremes of existence and the persistence of the human mind. They bend space-time, they warp causality, they challenge every certainty, and still, we reach toward them. We build machines that can feel the tremors of space. We stare at light that circles the abyss. We write equations that dance at the boundary of meaning. Why? Because something in us refuses to look away. Something in us is drawn to the edge, not for destruction, but for understanding. Black holes are not objects, they are events, they are transformations. They are stars that collapsed under the weight of their own gravity and became something else. Isn't that, in some way, a metaphor for all life? We grow, we change, we reach a point where the old rules no longer apply. And in that collapse, something new is born. Not always clearly, not always visibly, but something. And so we study black holes not just to map the cosmos, but to touch that process, the process of change, of boundary, of becoming. We are made of stardust, this we know. But perhaps we are also shaped by shadow, by the unseen forces that hold galaxies together, by the silent rhythms of collapse and rebirth, by the gravitational tides that whisper across time. Black holes are not the end of science. They are the beginning of wonder. Because even now, after all our discoveries, the greatest truths remain questions. What lies beyond the horizon? Do black holes connect us to other universes? Are they conscious? Are they machines? Are they mirrors? Or are they simply themselves majestic, terrifying, beautiful expressions of gravity at its purest? Perhaps we will never know. But perhaps that's not the point. Perhaps the gift of black holes is not in what they give us, but in what they awaken. The courage to ask, the humility to not know, the wonder to imagine. We live in a universe where stars die, where matter vanishes, where time stretches and space folds. And in that universe, we ask why. We build stories from silence. We build meaning from curves in space-time. And we listen carefully, tenderly to the music of gravity, carried on the waves of creation. Black holes do not speak, but in their quiet, they have told us more than we ever expected. They have told us that the universe is strange, that the universe is vast, and that the human spirit, small though it is, reaches even into the heart of darkness and dares to dream. So the next time you look up at the night sky and see a star twinkling from some distant spiral arm, remember, somewhere in the shadows, a black hole waits, not in menace, in mystery, and perhaps in that darkness we will find not just the limits of physics, but the beginning of something deeper, a question, a reflection, a light.